Okay, we're going to go over a couple theorems that have to do with integrals. These that have to do with mean values or average values. So the book definition is if we have a continuous function and it's closed from a to b, so there's no holes, somewhere between a and b there's a number c such that the integral that we evaluate from a to b is the same as just taking the value at c times the width. Okay, so basically what this is saying is the area under the curve is going to equal the area of some rectangle that's made by taking just the height of one value times the width of our section. Okay, so what that would look like is if I've got a curve like this, and I want to find the area maybe between here and here. Okay, well, we can do that with an integral, but the mean value theorem states that there's some value in here, maybe it's right here, this value of c, which would give me a height of this. Okay, so this one's probably not the right answer, but it would give me a height of f of c. They're saying is if I take the area of this red rectangle, then that would equal the area, the same area that I would get under the entire curve. Okay, so obviously I picked the wrong value of c because my area is going to be less, but they're saying that somewhere in there is a value that would give you the same. Maybe it's actually this value. Maybe this is our c that we want. Okay, so this red rectangle have the same area as the actual area under the curve. So that's what the mean value theorem states. And you get it just by, if you solve this, you'll get a number, and then you'll be able to solve for c. And I'll go through some examples where we're doing that. If we want to find the average value of a function, okay, we're basically going to take the same equation, and we're just going to divide both sides by this b minus a. Okay, because what this does, the integral, it takes all of our heights times our widths, okay, because we're finding area, and it adds them all up. Well, if we take and we divide that by the entire width, or you could think of this as the number of widths that we have, okay, we're taking an average, and that average is going to give us the average value of the function, which is the average height. Okay, so this gives us our average y value. This function does down here. Okay, because we're taking all of our areas added together, okay, and dividing by the number of areas that we added, and that'll give us our average value of the function. So let's go through a couple examples. So if I want to find the average value of the function and the value c at which this value occurs, okay, well, the average value of a function and the value where it occurs. Okay, so I can use this equation to get the average value. Okay, because this equals f at c. Okay, basically I just move this over to get this second equation. So I'm going to take 1 over b minus a, so that's going to be 1 over 3 minus 1, which is 2, times the integral of 9 over x cubed evaluated from 1 to 3 dx. Okay, and this is going to equal some number, which would be the same as the function at some value c. And I'll then be able to solve for c. Okay, so let's evaluate this out first. So using my integral rules, I'm going to change this a little bit to make it easier. I'm going to pull this constant 9 out. So I've got 9 halves. Okay, and instead of x cubed on the bottom, I'm going to change it to x to the negative 3 on top. Okay, don't forget your dx. Now, to evaluate this integral, I'm going to raise the power by 1, which will bring it up to negative 2, and drop the reciprocal of this. I've still got the 9 halves out front here. Okay, if I combine my fractions, I get negative 9/4. This x to the negative 2 is really an x squared on the bottom, and I'm going to evaluate that from 1 to 3. So if I plug a 3 in here, I'm going to get a 9 squared, or a 9 on the bottom. It's 3 squared, and that's going to cancel with the 9 on the top, so I get negative 1/4. And if I put a 1 in there, I get 9, so minus negative 9/4, which is really plus, and that's going to give me 8/4, which is 2. Okay, this is the average value of our function. Now, if I want to find out where this occurs, all I need to do is find out what value of x, okay, or what c value here in our function equals 2. Okay, so I'm going to reciprocate both sides, or you can think of it as cross multiplying. But basically, I'm going to get c cubed over 9 equals 1/2. If I multiply both sides by 9, I get c cubed equals 9 halves. And I cube root it. C is going to equal the cube root of 9 halves. Okay, which means if I find the area at this value, okay, so if I have a rectangle that's, so if I plug this in, so basically if I take f at c times 3 minus 1, which is my width, I should get the same answer that I get when I do the integral from 1 to 3 of f of x dx. So let's check that out. So if I do f at c, okay, so if I plug my c value in, I get 9 over the cube root of 9 halves cubed times 2. Okay, these cubes cancel each other out, so I've got 9 divided by 9 halves, which is the same as multiplying by 2/9 times the 2. I get 2 times 2, which is 4. So that's the value of this area. Let's find the value of this area. Okay, and I already integrated this, so I'm gonna just kind of use my answer from up above. Okay, but I'm gonna leave off this 1/2 because that 1/2 was us finding our average value. So if I leave that off, I'm just gonna have the integral from 1 to 3, 9 over x cubed dx. Pull the 9 out. Change this to negative 1/2 x to the negative 2, evaluated from 1 to 3. So I've got negative 9 over 2x squared, evaluated from 1 to 3. If I put the 3 in, the 9's will cancel, I'll get negative 1/2. If I put the 1 in, I'm subtracting a negative 9 halves, which is adding, which gives me 8 halves, which is 4. Okay, so this is the actual area under the curve, and at this c value, I get a rectangle that has the same area of the area under the curve. Okay, so I've got a couple more examples here. Okay, so here's one more example. So I want to find the average value of the function over the given interval, and I want to find all the values of x for which the function equals its average value. Okay, so first I'm going to find the average value. So I'm going to take 1 over b minus a and multiply it by the integral from a to b of the function. Okay, so b minus a is 2. So I'm going to half of this integral 1 to 3. And I'm going to have to rearrange this a little bit so I can integrate it. So I'm going to distribute. Okay, and I'm going to split that x squared up. So this is just going to be 4. Okay, and I'm going to split this integral up so I give it to each term here. So this one becomes half of, okay, so this is just 4x evaluated from 1 to 3. This is 1/2. Raise the power by 1, which will make it x to the negative 1. Drop the coefficient. And this is evaluated from 1 to 3. So if I put 3 in here, I'm going to get 12. Half of that is 6 minus half of 4, which is 2. So 6 minus 2 is 4. Here I'm going to have negative 1/3 times a half, which is negative 1/6, minus negative 1 over 1, which is negative 1 times a half, so minus negative 1/2, which is 3/6. So that gives me 2/6, which is 1/3. So I got 4 plus 1/3, which is the same as 12/3 plus 1/3, 13/3. So that's my average value. This is my average f of x. I want to know which values of my function, so which c values, equal my average f of x. So which values of c equal this? So I'm just going to take my function instead equal to this and solve. I'm going to use a simplified one too. Or actually, no, I'm not. So I'm going to cross multiply here. So I'll get 12 x squared plus 1 equals 13x squared. If I distribute, oops, this should be 12. Subtract this over, I'll get 12 equals x squared square root. So I get plus or minus. This breaks down into 2 square root of 3. So those are the values where my function equals the average of my function. Okay, so it's a little bit different than what they're asking for before. Before they're asking for the value where the area under the curve would equal the area created by that rectangle at that value. This, they're asking for the values that give you the same value as the average of the function. We could do it with cosine of x also. So trig function a little bit different. Just make sure, I'm not going to go through the whole problem, but just make sure when you're integrating trig functions, you have to ask yourself, what do I derive to get this? Well, cosine is the derivative of sine. So when you integrate this, it's just going to be sine of x evaluated from 0 to pi over 2. Okay, so if you have like the integral of um, secant squared x, well, I derive tangent x to get this, so this turns into just tangent x. Okay, so you're going to have to look at your trig rules, and they're all on the front flap of your book if you want to look. There's actually integral rules there too, and this one would be in there, and it would just say that this equals tangent of x plus c, I'm pretty sure. So that's kind of the ways you'll be using the mean value theorem to either find a value that equals the area under the curve or to find a value that equals the average value of the function.